Hello, Lee. Can you hear me?
I can hear you.
Sorry. Can we get the audio? All right. Sorry. I want to get.
I can hear you.
Okay, good. Yeah, I wanted to bring you on before I introduce you to the audience here. You should be able to see them through the camera here.
Yes, I can see the banquet.
All right. Thank you, Lee. So I want to introduce everyone here to Lee Morin. You could call him Dr. Lee Morin or Captain Lee Morin. Lee Morin was selected as an astronaut in 1996 on his first try, which is a very rare accomplishment. He holds several degrees, including a BS in mathematical electrical science from University of New Hampshire, an MS in biochemistry from NYU, a doctorate of medicine and a Ph.D. in microbiology from NYU, a master's in public health from University of Alabama at Birmingham, and finally an MS in physics from the University of Houston Clear Lake. He was designated as an undersea medical officer, qualified as a diving medical officer, qualified as a submarine medical officer, and designated as a naval flight surgeon. So that means that he's probably the only person you're ever going to see who, if you get sick at the bottom of the ocean, in space, or anywhere in between, he can take care of you. In addition to his time in the military, Lee Morin was in private practice in occupational medicine before volunteering for active duty in Operation Desert Shield, where he served as a diving medical officer / flight surgeon in Bahrain. He was director of warfare specialty programs at the Naval Aerospace and Operational Medical Institute. He served as a mission specialist aboard STS-110, where he logged about 259 hours in space, including over 14 hours in spacewalk. Also, he was appointed Deputy Assistant Secretary of State for Health, Space, and Science with the Department of State under the late Colin Powell. And he is currently assigned to the Exploration Branch of NASA JSC, where he is supervising the Crew Interface Rapid Prototyping Lab and basically working on the Orion Multipurpose Crew Vehicle. Did I leave anything out, Lee?
No, that sounded great. Thank you.
All right, thank you. So with that, I would like to turn it over to our speaker. And at the end, hopefully we have a little bit of time if anyone has any questions. So thank you.
Great, thanks. Well, it's a great honor to be here with you today to share some observations about how my colleagues and I's experience in spaceflight have been illuminated by our physics education. I apologize for not being able to appear and participate in person. This is one of the many cruel consequences of COVID, and NASA remains hypervigilant in protecting flight crews and those who may interact with them. From the first milliseconds of ignition until the rollout comes to wheel stops or parachute descent terminates with touchdown, every aspect of an astronaut's success and fate are guided by the laws of physics. As we move into the third decade of our new millennium, let's take stock of where humanity is with respect to getting into space. We will emphasize three main areas. First, with the International Space Station, we have the largest international engineering collaboration ever, which has resulted in permanent human presence in space during this entire millennium, and in all probability, permanent presence, period. Second, a key part of NASA's charter from 1958 is to promote commercialization of space. Over the past decade, NASA has nurtured a flourishing commercial crewed space industry, as Captain Clarke can attest, with vigorous competition that encourages progress and pragmatism, aggressively applying the free enterprise model to great effect, even upon NASA itself. Third, we're about to commence an ambitious program of exploration. I personally have had a minor role in this program and would like to outline our pending exploration program and describe the physics underpinnings. The Artemis Exploration program will return humans to the environs of the moon and set the stage for missions to Mars. With ISS, we are 250 miles from the Earth. At the moon, we are 250,000 miles from the Earth. And at Mars, we're 39 million miles from Earth or more, a fierce scaling of distance, duration, difficulties, and risk. The Orion spacecraft is a vehicle that will get crews out to cislunar space and return them to Earth. The next test flight is scheduled for February 2022, coming up in a few months. In this picture, we can see the capsule, the launch abort system with its protective shroud, which will extract the capsule from a catastrophic launch mishap. And finally, behind, we have the European service module with oxygen, water, fuel, engines, and solar cells to provide 18 to 21 days of endurance for Orion. This is a view of the Orion Cockpit mock-up in Building 9 at the Johnson Space Center. My role has been to lead the team that prototyped the crew displays you see here, shown on the 3 display units or DUs, and those are these computer screens up across the top. These are the computer screens that the crew used to monitor and control Orion throughout each mission. The next test flight is Artemis 1, as I mentioned, scheduled for February of 2022. This mission will place a spacecraft around the moon and back, a spacecraft capable of transporting humans into deep space and returning them back to the surface of our hospitable planet for the first time since 1972. The February launch will be the last uncrewed mission. Artemis 2 will be the first crewed flight of Orion. Up to 4 astronauts will return to the lunar environment for the first time in more than 50 years. This will be the Artemis generation's Apollo 8 moment, when the astronauts aboard Orion will capture the full globe of the Earth from afar as a backdrop to the moon. Subsequent annual Artemis missions will rendezvous with Gateway, a habitat to be staged in an orbit near the moon. Our current ISS partners will provide important contributions to Gateway, comprising advanced external robotics, additional habitation, and possibly other enhancements. The Artemis program will transfer crews from Orion to the lunar surface near the South Pole, dubbed to be the most valuable real estate in the solar system, with near perpetual sunlight, continuous direct communication with Earth, and the promise of billions of tons of water trapped in the 50 degrees Kelvin permanently shadowed craters at the lunar poles. This is a picture taken by the ESA Smart 1 mission of Shackleton's crater at the South Pole, which has a rim of near perpetual sunlight. However, sunlight has never illuminated the interior of the crater itself in all the time of the history of the moon. And there's extensive water down there. And this crater is very large. It's over 21 miles across, and it's 20 times deeper than the Grand Canyon. So this is quite a geological feature. Here at the South Pole, we can envision the Earth and Sun permanently on the horizon with long shadows illuminating vertical solar arrays. Let's take a closer look at some of the aspects of the mission and see how our physics education ties in. Before we can go anywhere, we have to have propulsion. We are at the bottom of a gravity well. To get off the planet and to be able to stay off, to get to orbit and beyond, we need to achieve sufficient speeds. Changes in velocity, or delta V, are the coin of the realm in spaceflight. Of course, the energy required rises as the square of the delta V. To stay in space, to get to orbit, requires a velocity of Mach 25 or 25,000 feet per second. At Mach 3, Captain Kirk had only about 2% of the energy needed to stay in space. The physics of attaining delta V with a rocket engine is covered by the famous rocket equation summarized here. The ability of a propellant to provide delta V in a rocket engine is measured as specific impulse, or ISP. For chemical rockets, where the propellant itself provides the energy of propulsion in chemical bonds, ISP is limited by the energy available within those bonds. This limitation, together with the gravitational properties of Earth, dictate that a rocket must be 85% fuel to get to orbit from our planet. If the planet was 50% larger, we could not get to space using chemical rockets at all. There would simply not be enough sufficient energy in the chemical bonds of any propellant. ISP is also related to the square root of the temperature, which you can see in this equation here. It's related to the square root of the rocket exhaust, and the hotter the better, which presents real material engineering challenges to rocket construction. For the highest ISPs, their exhaust is hotter than the surface of the sun. This is a view of the booster of the Space Launch System, or SLS, that will propel the Artemis missions off the Earth. It uses 4 instead of 3 Space Shuttle main engines, and these are engines left over from the Space Shuttle program. The engines on the shuttle were intended to be reused up to 100 times. These will be used only once, and so they can afford to really push these engines from the 100% up to the 104 that was used for Orion, up to 109 that could be used in an emergency, and even up to 113% to get as much performance as possible out of these engines. These engines protect their nozzles by cooling them with liquid hydrogen in a network of tubes and passages you can see if you look closely in these areas here. It's part of the nozzles. Liquid hydrogen temperatures in those tubes are a few centimeters away from solar surface temperatures inside the exhaust. Once one does get to space, there is a severe radiation environment to contend with. This slide shows the Van Allen belts, which concentrate particles in the magnetic fields around the Earth. These present a severe hazard, and one wants to pass through them as quickly as possible. In addition to the Van Allen belts, they're both galactic cosmic rays and solar particle events that produce energetic particles with long-term effects on both humans and on the complex electronics the missions depend on. To monitor these radiation hazards, there's a new imaging sensor technology from CERN called TimePix. The CERN-developed TimePix detectors is being used by NASA aboard the Orion spacecraft. The TimePix sensor is a 2D photo imaging array similar to a cell phone camera that records particle tracks, which is like a virtual 2D bubble chamber. Analysis of the images provides spectral data of the radiation flux. Exposures are integrated to provide dose and dose rates to alert the crews if a high radiation solar particle event should occur. Once alerted, the crew can rearrange the cabin and shelter within lockers to reduce their exposure to half of what it would be if they remained unsheltered. This instrument was flown aboard the ISS, as we can see in this photo of Megan. And here you can see up here on the bulkhead, this purple instrument. That is the Hera hybrid electronic radiation assessor implementing the TimePix sensors. This is a close-up picture of the instrument. The main electronics package, the big purple box in the middle, has one of the 2D sensors. There are 2 additional 2D sensors in these purple areas on the side, on the left side and on the bottom. So altogether it has 3 sensors which are arranged at right angles, and by having those 2D sensors at right angles, there's additional information that's provided about the flux. And the data from the Hera sensor is captured every minute, and that can be collected over time as the ISS orbited the Earth. And this data was taken and actually was analyzed in a student outreach program in England. What the students were able to determine was the prominence of the South Atlantic Anomaly, this yellow region here over Argentina and Brazil and the South Atlantic Ocean, which is a hotspot where the Van Allen belts come the closest to the Earth, and the International Space Station passes through these belts on some of the orbits that hit it. And so it's possible to view the sequential images that you can see here. And here you can see the particle tracks. And depending on the orientation of the particles, you'll have lines or dots. But these will increase as you go through the South Atlantic Anomaly. And the students were able to do a lot with the mapping the different types of information in the images against the map data, and provided a lot of fascinating insight into the radiation environment. Passing through this area can also result in lockup of laptop computers, as astronauts will tell you. And this radiation can have severe impacts on critical electronics. Now, this is a picture of Arthur C. Clarke's Milestone book, which popularized details about what's involved with spaceflight, which was published in 1950, long before Sputnik. Here is one notable quote. The orbit will be calculated by ground stations in radio contact, so more powerful computing equipment can be used than could ever be carried on a spaceship. I recall naively scoffing at this prediction in the 1970s, but remarkably, this prediction from 1950 is still true in the 2020s. The radiation environment is very difficult for the electronic devices we take for granted. Ones that are reliable enough to bet your life on in the high radiation environment have pretty limited capabilities to compute the highly iterative dynamic programming solutions required for interplanetary flight. Much of the capability we do have on board provides redundancy to ensure that the state vector and other key information aboard Orion is never lost. And in fact, 8 computers back each other up in the Orion spacecraft. Usually, the theory of relativity involves velocities far removed from everyday life. However, the development and wide adoption of the Global Positioning System, GPS, has put a relativistic system at our fingertips, as Dr. Garrison taught me. A GPS satellite can be seen on the cover of this textbook. Of course, classical mechanics is the bedrock of physics education and provides the foundation for more advanced dynamics, such as the new methods of celestial mechanics pioneered by Poincaré over 100 years ago. This work led to the emergence of chaos theory starting in the 1960s and on to a voluminous literature on the geometry of the dynamics of orbits and chaotic behavior. Celestial mechanics and ideas of chaos theory underpin the emerging science of deep space navigation and interplanetary travel. The key concept of interplanetary travel involves the Lagrange points first identified by Euler and Lagrange hundreds of years ago. These are the gravity null points around each astronomical body, which can serve as stepping stones from one planet to another. Between the Lagrange points, navigation is possible that requires remarkably little delta V. Between these points, one is sailing on the edge of chaos. These techniques were used to map remarkably complex orbits during the Genesis mission, which orbited the L1 point, the L1 Lagrange point, to collect solar wind samples and then return them to land in Utah in 2004. But you can see how complicated the dynamics of these orbits are. Important research on these topics continues to this day. And it looks like there's arches of chaos that will map out fast transport for the solar system. Coming back to Gateway, this shows a artist depiction of the Orion docking with a Gateway vehicle out near the moon. The Gateway vehicle will be placed in a cislunar orbit by one of NASA's commercial partners. It will be home to crew 1 month a year. The rest of the time it will be tended from Earth. As most long-duration deep space vehicles, it will rely on electric propulsion, where the energy is not provided by chemical bonds, but rather by external electrical power generated by solar cells. This permits a higher ISP, which greatly economizes fuel, but does so at the expense of very limited thrust. Limited thrust, but adequate for the modest nudges over long periods of time that are sufficient to maintain and adjust a deep space orbit and to maneuver as needed. Of course, electric propulsion begins with electrodynamics, a subject close to every physics graduate student's heart. Plenty of electrodynamics and plasma physics form the foundation for plasma propulsion. This is the Gateway's power and propulsion element, the PPE. It is a 60 kilowatt class spacecraft with 50 kilowatts dedicated to the solar electric propulsion engine and the other 10 kilowatts dedicated to spacecraft power. Finally, we need to come home. On return to Earth, we have to dissipate the immense energy from the velocities we have obtained on leaving. This requires a heat shield sized to deep space velocities. Orion will have the largest heat shield so far, 5 meters in diameter, to dissipate velocities of Mach 32 or more on lunar return, compared to Mach 25 from low Earth orbit. So the astronauts will be getting some new passages with bigger numbers, and I'm sure there'll be one-upmanship about who has the biggest number on their patch. There are plenty of thermal and, again, plasma physics involved with understanding re-entry and how the heat shield really works. And finally, we have the last steps of re-entry. For the last mile of the mission, literally the last mile, because the parachutes are deployed between 5,000 and 6,000 feet of altitude, the crew would descend at 20 feet per second under a triple canopy of parachutes. For a capsule, the final impact with the welcome ocean surface needs to be attenuated, with a correctly oriented capsule chipping into the water and with tuned impact attenuating struts providing the crew seats with occupant protection against a potential hard landing. And this is a test facility that was used, that's up at the Langley NASA facility in Virginia. And this facility was used to test the Apollo capsules, and it's still in service and is used with today's capsules, as you can see, for Orion. This is a video of the tests on Orion with a video of the capsule entering the water and also a view of the mannequins on the seats where they're attenuating struts, which you can see down here, that absorb some of that shock to protect the crew. Much work has been done in this area, including a partnership with NASCAR experts that was very helpful. Although they had one suggestion that landing without parachutes would be a survivable option, since NASCAR drivers are protected, have been protected during crashes of comparable speeds. I think we were all relieved that this option was not embraced by NASA. So here we see an image of the Orion capsule entering the Earth's atmosphere, dissipating the Mach 32 to 38 tremendous velocity with an ablative heat shield that actually particles of the heat shield flake off by design to dissipate this energy and provide the crew a safe ride home. And with this, I do have some websites up here for those of you that are interested so that you can come in on social media and connect with more details about the Orion and NASA missions. So I've been very grateful that Dr. Garrison gave me the opportunity to share with you some perspectives of how my physics education underpins understanding of so many surprising aspects of spaceflight. And with that, I think we can go to questions.
All right. Thank you very much for that wonderful presentation. Can I get any questions? And I can repeat them so that Dr. Morin can hear them over the Zoom session. Yes. Sorry.
Hi there. Can you hear me?
I can.
Okay, so my question is, why did you switch careers so many times, or why did you try so many things?
Yeah, I guess I can tell you that when I was a student and applying, I was accepted at the MD Ph.D. program at NYU. And I told my grandmother, and she told me, Lee, I'm so relieved that you finally found something that you can do. So I guess I'm, still looking for some, for the gusto and looking for more exciting things to do.
Oh,
Yeah, so the question is, what is one of the challenging thing of being an astronaut?
Right, what's the most challenging thing of being an astronaut? Probably the most challenging thing is getting selected. And I know we just selected and are going to very soon announce 10 astronauts to the new class of 2022. And we interviewed and reviewed 18,300 applicants. So it's really, that's probably the most challenging thing is getting picked. Once you're picked, I think the challenging things vary depending on what your background is. For me, I certainly found it challenging learning how to function as a crew member on board one of our T-38 jets. And I had relatively little flight background. I was a Navy flight surgeon, had a few hundred hours, but it's nothing like the thousands of hours that our test pilots arrive with. The test pilots were challenged by other things. They found the flying part easy, but there's something difficult for everybody, and all our skills blend together. The thing that NASA really stresses is that we all have strengths and we all have weaknesses, and the goal is to train a crew so that they work and look out for each other and help each other, because that's what they're going to need to do if they're 250,000 miles from Earth and things start to go wrong. We're going to need every bit of skill and creativity and talent and knowledge that the crew has together. And so those are some of the key lessons, is really learning how to work together as a crew and leveraging everyone's strengths.
Hey, it is so good to see you, by the way. This is Meena Masood.
Great to see you, Dr. Masood.
Yeah, and I think that I should say that we can genuinely be proud of you as a student in the UHCL program of physics program. Anyway, I have a question here that you said that there are plannings that man will land on moon in 2022, 2024, sorry. So what kind of, can you give a little bit more idea that what is in the plan, that how long it will take to get there, and how they plan to make the moon habitable for human beings?
Yes, so I get an overview of that. So there is another program called HLS, so the Human Landing System. That was a commercial where NASA invited companies to bid on that and prepare preliminary versions of that. And in fact, my lab worked with two of those companies to develop a prototype cockpit for their moon lander. I can't show that because that's still proprietary and there's still questions about the contracts. But the idea is that there will be a lander vehicle that will take crew from the Gateway and from Orion and go down to the surface of the moon at the South Pole. And we'll land there and we'll stay there about a week. And the crew will go outside and do spacewalks and gather samples and begin the process of exploring and answering the question of, is there abundant water in the craters of the moon, and many other questions. And the South Pole of the moon has areas that geologically extremely interesting about the early history of the solar system as well, that the geologists can really inform you about. So those are some of the things. And the idea would be to start building up an infrastructure so that you could have a sustained presence and reuse the facilities that you leave and build up a concentration at the South Pole. As I mentioned, the purpose of the South Pole is that the moon is not tipped on its axis very much the way the Earth is. And so the South Poles remain at the, sort of pointed down, so to speak. And from those poles, you have a near permanent sunlight, and you also have shadows that are permanent for the craters, which is why the water collected there. A giant cold trap at about 50 degrees Kelvin, and the water diffused in there and can't get out. Billions of tons of water potentially down there, determined by various studies, including radar imaging and other imaging, as well as dropping a booster and kicking up a cloud of water that was a cloud of dust that had ice in it. And so those are some of the reasons that they're going. The duration on the moon will be about a week for the first missions. There'll be a special vehicle called the HLS that will descend from the gateway. Orion will go down and meet it partway up. Orion doesn't have enough fuel to go all the way down into low lunar orbit. And unlike Apollo, where we had the Apollo crew module and service module were in an orbit around the moon, the HLS will have to come up to a higher altitude, and the Orion will go down, and the crew will be transferred from the HLS into the Orion, and then they'll come home. So it's a combination of using the gateway, using Orion, and using the HLS lander, which hopefully we'll be able to have a lot of discussion about that soon as the contracts are finalized, and we'll be able to talk about that in more detail.
Okay, I have a question. I just wanted to know what advice you could give to graduate or undergraduate students who might eventually want to end up at NASA, just your 2 cents.
Yeah, so, the key there is to do the best work you can, be good at what you do, fit in with the people around you so that you have a reputation of being a team player, being a go-to person, being a cheerful, upbeat person that works with people, gets things done, have intellectual curiosity, broaden your interests so that you become established or knowledgeable about different fields. And if you are interested in actually, in a flying role, you need to get aviation experience and show that you're comfortable in aviation, and that you are able to work in what we call an operational setting. An operational setting is one where you have to make decisions that have real consequences in a time-compressed environment. You could have someone who'd be a brilliant scientist, and you give that person a problem, and in 2 weeks they could give you the answer and win the Nobel Prize. But in the space business, you may have 10 seconds to make a decision and flip the switch or not flip the switch, and you don't have 2 weeks to do it. So you've got to be able to do psychomotor things involving flipping switches, flying airplanes, and doing other operations like that show that you can perform under pressure and in a time-compressed environment, keep your head and get the mission done. So that operational experience is very important. And there's many different ways to do that, but that is a key aspect of that. Another aspect is people that show that they work well in an international environment, that they're involved with outreach, they're involved, comfortable working with other cultures, other languages, knowledge of language, interest in people in general. those are all the sorts of things that are pluses.
So my question was, during your time in space and all your spacewalks, was there a specific site that was kind of awe-inspiring to you that really took your breath away?
Yeah, I can think of one. On the shuttle in the payload bay, there were some cameras, and they had just introduced a new kind of light. It was now they're commonplace, but it was a ring of LEDs that went around the camera lens. And that was, it was a new camera that I think that may have been the first time that camera light was flown. And those cameras were down in the payload bay, and it was dark, and those lights were on, and they looked like two halos. And I was on the end of the arm out over, moving around the space station and moving over the shuttle. And I looked down against the blackness and saw the payload bay against the blackness of the Earth below. And I saw those circles, and it said, boy, it looks like there's two halos or angels in the payload bay. And they came back, Lee, could you check the oxygen in your suit? So, I said, no, I'm just looking at the lights in the camera, and my oxygen and carbon dioxide levels in the suit are good. So that was one little thing that startled me. But certainly the most spectacular thing is looking down at our planet Earth. Watching the sunrise, which happens 16 times faster than it happens here, where first you just would see a little bit of haze across the horizon as the sun starts to come up. And then it would come up, and it would be almost like if you can imagine in a play where they put on the Klieg lights and they just go to a very dark red. And I remember looking down and seeing the Soyuz spacecraft just being you could hardly see it, with a little bit of reddish orange that lightened up to a yellow, and then blam, it was full on bright, like in the limelight. And I remember that being a very spectacular thing. Look, and I'll tell you, one of the things that really struck me, and I noticed that as we had some of our commercial colleagues comment on this recently, is looking out, and you can see it on the thing behind me, the edge of space there, the atmosphere. You can take a pair of binoculars and look at that, and you'll see up to 7 layers of the atmosphere. And you look at that atmosphere and you see how thin it is, and how puny it looks, and how much we depend on it. And that was something that struck me. And I noticed that I think Captain Kirk, William Schaffner, commented on that. And that struck a thing with me, is seeing the layers of our atmosphere, and the part that's thick enough to breathe is only about 2 miles thick. You go above about 2 miles of altitude and you start, not having enough air. I guess there's a few places in the Andes where you can go up to maybe 3 miles, and above that, you're going to need to be on oxygen if you're going to be there any time. And if you scale that to the size of the Earth, it's like the thickness of the film of the soap of a kid's soap bubble. And that little film of the soap bubble is our film of atmosphere that we depend on, and it makes you want to do what you can to protect it.
Going through the entirety of NASA's future mission timeline.
I think he's a little.
I'm sorry, I'm not hearing you clearly.
With you going through the entirety of NASA's future mission timeline, is there anything you'd like to see NASA accomplish that you didn't cover?
Well, there's one thing that is sort of a pet project of mine, which is to, and I think this will come out of our moon missions, and that is really extensive insight to resource utilization on the moon. And I know Dr. Garrison knows that this is a sort of a pet theme of mine. In fact, we had talked about that being rocks to robots, of really building up an industrial base on the moon, exploiting the sunlight and materials that are there to form ceramics and extracting metals to actually build up the infrastructure we need in space. And if you look at the difficulty, most of the energy that's required to get into space happens just to get into low Earth orbit. Once you're in low Earth orbit, it's whether you're going from there to the moon or to a geosynchronous satellite or even to Mars, it's not much difference in the delta V. It's bringing stuff up. And so if you can avoid bringing up stuff that's heavy, like fuel and oxygen and bricks and make, structural elements of spacecraft and so forth, if you can make those in place, you're going to be much better off. And that will be the key to really having an explosion of in-space capability and permanent presence. And so I hope that NASA does a lot of, they call it in situ resource utilization, ISRU, using solar furnaces to fuse regolith into glass. Actually, regolith glass is so anhydrous that it is up to 50 times stronger than Earth glass. So it'd be a marvelous material. All sorts of things. And so that would be an area that I hope NASA, and I hope that becomes a commercial enterprise. I could see a whole robotics community with companies selling services to each other and building up a huge commercial enterprise like we're starting to see with low Earth orbit services, as I showed before.
I have a just question or something you can talk about. I remember before you talked about a long time ago about sleeping in space and how you could actually see these cosmic ray. Could you tell the audience about that?
Yes, absolutely. So when you sleep in space on the shuttle, you had a little bag. It was sort of like a sleeping bag, only it was a thin material. And you had cutouts so your arms would kind of float in front of you, and you'd assume a fetal position, and you would float there. And then that little sleeping bag had some straps that you would tie off on some pipes or the bulkhead, and you would just kind of float there. And as you were sleeping, you could, before you fell asleep, you could see flashes going through your eyes. And there would be these bright flashes, and sometimes and you could almost get a sense of the lines, just like we saw on that 2D sensor where sometimes you saw lines and sometimes you saw dots. Just imagine those are your retina being stimulated by the Cherenkov radiation of particles decelerating as they go through the vitreous of your eyeball, and you would see these flashes. Could sometimes be in different colors, and if you were in the South Atlantic anomaly, there would be more of them, and you could see those flashes. Another thing that was striking about floating in space is that as you fall asleep, we all twitch a little bit, and as you fall asleep, your knee might twitch or your elbow might twitch, a familiar thing we've all experienced. In space, when you're hanging there, when you twitch like that, there's a Newton's law that you recoil and you bounce around inside the sleeping bag that could be quite startling from that twitching. So those are the two striking things about sleeping in space. The other is that once you're in space for a while, it starts to feel like this is the normal way of things. And after a week or two in space, it seems really odd to think about walking, just sort of floating. And I don't know whether it goes back to experiences in the womb or whatever, but it seems very natural to be floating. And it seems like that's the way things should be. And I remember getting out of the sleeping bag in the morning. You just would take two fingers and slide right out, and then float over there to go into the restroom or whatever. But when you came home, and we were sleeping in a hotel in Florida, the first night, I woke up and I was still in space. And I went out of the bed and just floated out with two fingers and soared like a gazelle, but I didn't land like a gazelle. And so it takes a day or two to get used to being back on the planet. A little bit like when you first get off a deep sea fishing, if you're deep sea fishing and you come back and you walk on the dock and the dock seems like it's moving, well, that's the way the runway felt when it first walked off the spacecraft, and takes a couple days to get your Earth legs back.
All right. I think we have time for one more question, and then unfortunately we have to move on to our next part of the banquet.
So what is the most difficult scenario that you faced, and like how you solved that scenario?
The most difficult scenario that I faced, um,
Problem.
probably the most difficult scenario I faced was on the second EVA when the ground completely changed what they wanted us to do. We had to do some different tasks. And and I remember it came up, there was a printer on board and it came up sort of about 20 pages of new tasks that we needed to do. And the time to do it was coming up. So it really took some intense study to make sure that we were prepared to do that. And for that, I remember there's the Russian BAO module is a sphere, and it has a window that looks forward and back, and it has bungee cords stretched across it. And I remember holding onto the bungee cords with my big toe, like a spider, hanging on those bungee cords in the middle of that thing, studying this thing to make sure that knew how to do all those tasks that I needed to do for the space station the next morning. That was probably the most challenging experiences, that shift of gears and getting ready for a pretty different lineup of tasks for the EVA, my second spacewalk.
All right. So let's thank our speaker. All right. And thank you, Dr. Morin. Our next part of the program, I believe, is going to the awards. So thank you very much for talking to our banquet.
Thank you. My pleasure. Hope to see you again soon, Dr. Garrison.
Hey, hope to see you too soon. Bye.